Mathematical methods of physics. Welcome to VK lectures. In this lecture we will be discussing about complex integration, where we will also be finding methods how we can get the residues of a complex number, and from residues we will find how to find the integral of a complex number using Cauchy residual theorem. Here we are going to see the complex integration with the function f of z with the pole of order n plus 1, which means you have the function integral f of z by z minus a whole to the power n plus 1 dz. This is what is called a pole of order n plus 1. Now this is equal to 2 pi I times the nth derivative of the function f of z at z equal to a. Now this is for pole of order n plus 1. For pole of order 2, we get integral f of z divided by z minus a whole squared dz is equal to 2 pi I into fn. So it's f1 or f dash of z at z equal to a, and to have one more pole of order 3, which means the integral f of z divided by z minus a whole cube dz equal to 2 pi I divided by, here we have missed one term, that is n factorial. Here we have 1 factorial, here we have 2 factorial. Kindly note there is a term by n factorial here. This would be f double dash, which indicates the second derivative of z with z equal to a. So here what we need to understand, this fn of z is nothing but the nth derivative of f of z. Now if you want to find out the integral f of z divided by z minus a into dz, this is equal to 2 pi, this is what we have seen so far, 2 pi I into f of z at z equal to a. There is no derivative here. This is function as it is, closed integral. Integral closed integral over c z square plus 1 divided by z square into z minus 2 dz, where c is a circle with mode z equal to 1. Now take the denominator z square into z minus 2 and put it equal to 0, which means either the first term z square equal to 0 or z minus 2 should be equal to 0. When z square equal to 0, we can write z equal to 0, and for z minus 2 equal to 0 means z equal to 2. So there are two values for z, either z can be equal to 0 or z can be equal to 2. Now here the radius is given to be equal to 1, which means it should be within the radius, so z equal to 0. Z equal to 2 means it is outside the radius. So if this is the circle, this is the center, which is 0 0 according to the question, because actual how do you define the Z, the radius? Z minus x plus iy equal to the radius. Here x plus iy is 0, so both x and y are 0 means it is the center. Now this is the radius, which is equal to 1. Now the point z equal to 2 is lying outside the given circle, and z equal to 0 is here. So only point which is inside can be taken. So this is in, this is out. So our but z equal to 0 has a pole of order 2, the power is 2. So the z equal to 0 has pole of order equal to 2. So our integral takes the form z square plus 1 divided by z minus 2 divided by z square dz. Now since it is pole of order 2, we can write this is equal to 2 pi I divided by z square, means n plus 1 is 2, so n will be 1 factorial. First derivative f dash of z at z equal to a. What is a? 0. Pole is 0. Now that can be written as 2 pi I into d by dz, first derivative of whatever is in the numerator, z square plus 1 divided by z minus 2 at z equal to 0. Now take the first derivative of this function. So this is u by v differentiation, that's equal to v into derivative of u plus minus u into derivative of v divided by denominator, or that is v squared. So v is z minus 2 into derivative of u, that is 2z, minus u is z square plus 1 into derivative of the denominator is 1 divided by z minus 2 squared, and this is at z equal to 0, which implies, put z equal to 0 here, the first term goes to 0, this is minus 1, so minus 1 divided by, put z equal to 0 here also, 2 square, so that becomes 4 into 2 pi I, that is equal to minus pi I by 2. Integral cos square z by z plus pi by 4 whole square, this is over the c, and the circle is given as mod z equal to 2. Now take the denominator, we have z plus pi by 4 whole square is equal to 0. Now which means what? Z is equal to minus pi by 4. Okay, z is equal to minus pi by 4. Now what we have to do is, this is pole of order 2, so pole of order 2. So let's write down the formula. Integral, closed integral, cos square z divided by z plus pi by 4 whole square dz is equal to 2 pi I divided by, since it is 2, this is 1 factorial, d by dz of what is in the numerator, cos square z, at z equal to minus pi by 4. Now that's equal to pi I, first derivative of cos square z, that is 2 cos z, cos z derivative minus sin z at z equal to minus pi by 4. So that's equal to 2 pi I into 2 cos of minus pi by 4 into minus sine of minus pi by 4. This is into, okay, that's equal to 4 pi I. Cos of minus theta is cos theta, so cos pi by 4 is 1 by root 2 minus, so sine of minus theta is minus sine theta, minus of minus plus, so that is again 1 by root 2. So that's equal to 4 pi I divided by 2, that's 2 pi I. Here we are going to see what is singularity or singularities. Now if f of z is an analytical function in the domain D, now let us say we have the function f of z and this is defined in the domain D, then f of z is differentiable and continuous in this domain. So every point in on this domain is differentiable and at that particular point it is continuous. Now what do you call a singularity? Singularity is when f of z is not defined, when you cannot define the function f of z at a particular point, then we say that there exists a singularity. Now for take the case of an example of f of z is equal to z by z minus a. Now at z equal to a, now look at this, at f of z equal to z divided by z minus a, and now when z equal to a, our function f of z will be equal to a divided by 0, which is equal to infinity. Now this cannot happen because it is not continuous at a point. At, for example, this, let it be this z equal to a, at this particular point it is not defined. Now then that particular point is called singularity, singular point. Okay, where the function is not defined, the function can be 0 by 0, or the function can give infinity, or x by 0, or some quantity by 0. That means denominator should be 0. We also have seen that at that particular point f of z is f of z at z equal to a is not analytic. And now here we have given the point a term, that is singularity, where the function is not defined or the function goes to infinity. Isolated singular point. Now let's understand what is this isolated singular point. To understand that, let us take an example where f of z is equal to z by z minus 1 into z minus 2 whole squared. Now take the denominator here and put it equal to 0. So what is that? Z minus 1 into Z minus 2 squared is equal to 0, which means either Z minus 1 should be equal to 0 or Z minus 2 should be equal to 0. So if Z minus 1 equal to 0, and the possibility is Z minus 2 equal to 0. Now if when Z minus 1 equal to 0 means Z equal to 1, and here Z equal to 2. Now for example, this is the f of z where this function is defined. This is the domain D where this f of z is defined. Now let's say this is where the point z equal to 1, and say this is a z equal to 2, and at these 2 points z equal to 1 and z equal to 2, the function is not defined. They are called isolated singular points. They are isolated because they do not have any singular points nearby. So what is this isolated singular point? The singular point, the definition is singular point which do not have many singular points in its neighborhood. Okay, in the vicinity of the z equal to 1 and z equal to 2, they do not have much, they do not have many singular points. Okay, so they are called isolated singular points. Now let us see what is non-isolated singular points. Let's take 2 examples here how non-isolated singular points look like. Now f of z equal to z divided by e to the power z minus 1. Now as usual, take the denominator, which is e to the power z minus 1, and put it equal to 0, which means e to the power z equal to 1. So if e to the power z should be equal to 1, which means the z should be 2n pi I, because we know e to the power I x is equal to cos x plus I sin x. So e to the power equal to e to the power z equal to 1 means there is no complex term, so this part can be removed. So e to the power z should be equal to cos x. So if cos x equal to 1, then x value, so here we can write e to the power z should be equal to e to the power z should be equal to e to the power I 2n pi. What are the values of n? N can be equal to 0, plus or minus 1, plus or minus 2, etc. So here for many values of z, you get e to the power z minus 1 equal to 0. So they have more number of singular points, so they are called non-isolated singular points. Now take the second case here, f of z equal to 1 by sine of 1 by z. Now the denominator becoming 0 means sine of 1 by z equal to 0. Now sine of 1 by z, which means 1 by z should be equal to, it should be of the form n pi or plus or minus n pi. Now here we need z, so z should be equal to 1 divided by or plus or minus n pi. And what are the values of n? N is you can be 0 comma plus or minus, no, it n cannot be 0. If it is 0 it goes to infinity, so it cannot be 0. So plus or minus 1, plus or minus 2, plus or minus 3, etc. So this is what happens in non-isolated singular points. That means the singular points which has many singular points in the neighborhood. So that is what is mean by non-isolated singular points. That means they are in a cluster, they are in a group other than the isolated case. This is a kind of singularity where you can remove the singularity. So in effect there is no singularity here. So good example is f of z equal to sine z divided by z. In just while the appearance of this f of z, you can say that at z equal to 0, the function is not defined, so at that particular point we have the singularity. But sine z can be written as z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial, and it goes on. So this is an expansion of sine z. Now what is sine z divided by z? So that gives us 1 by z into z minus z cube by 3 factorial plus z to the power 5 by 5 factorial, etc. Now just multiply this with the z. So what you get is 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial minus z to the power 6 by 7 factorial, etc. Now here when you look at this function f of z, we have rewritten the function f of z in terms of series. So now we do not have any singularity because denominator do not contain z. So when the denominator do not contain z terms, which means there is no principal part, there is no principal part of the function f of z. Here is only analytical part. This is the analytical part of the function f of z. So that is called a removable singularity. Essential singular point. Now the essential singularity is a type of isolated singularity. So isolated singularity means for example in the domain we have the function f of z, which is analytic in the domain. This is the domain, and here we have a point a, which is uh, isolated singular point. It is isolated if there is no other points near neighboring the a where the function is not analytic. Okay. So in this essential singularity, or at a point, if the function is function has an essential singularity, then it is true that the function cannot be analytically continued in that neighborhood of that point. Now mathematically, if f of z has an essential singularity at z equal to a, it means that neither the limit z tends to a f of z, nor the limit uh, z tends to a, this is f of z, 1 by f of z exists. So f of z at z equal to a and 1 by f of z at z equal to a do not exist. Okay, these both functions do not exist in that neighborhood. All right. Let us assume that we have a function f of z, which is having isolated singular point at z equal to a. At z equal to a, we are having the function a singular point. Then, according to Lorentz series, we can expand f of z. Our function f of z can be expanded by Lorentz series at z equal to a, and this is how you can expand this. F of z can be written as sum over n equal to 0 to infinity an times z minus a to the power n plus sum over n equal to 1 to infinity bn into z minus a whole to the power minus n. The first part is the analytical part, and the second one is the principal part. The value of an and bn are given as an equal to 1 by 2 pi I integral f of z by z minus a to the power n plus 1 dz. That is n starts from 0 to infinity, so 0 a0 a1 we will have. Similarly, bn, which is the coefficient of the principal part, which is given by 1 by 2 pi I integral f of z divided by z minus a to the power minus n plus 1 dz. Here n starts from 1 to infinity. Now, assuming that we have at z equal to a, the function f of z has an essential singular point, then we can write f of z in the Lorentz series form: sum over n an z minus a to the power n plus sum over n equal to 1 to infinity bn z minus a to the power minus n. Here this can be written as n equal to 0 to infinity. Now this is the principal part. We'll take the principal part now one by one. That is b1 starting with n equal to 1 z minus a to the power 1 plus b2 into z minus a to the power minus 2 plus b3 into z minus a to the power minus 3. Now this goes on. Now the coefficient of z minus a is called the residue. So residue at f of z at z equal to a is nothing but b1. So our aim is to find the residue of the function. So this is meaning is residue of the function f of z at z equal to a. So that's from this b1 is the residue. Yeah, we have a question that is f of z equal to e to the power 1 by z. Find the residue. So when we write e to the power 1 by z at z equal to 0, we have f of z equal to infinity. So this is at at z equal to 0, we have the singular point where the function is not defined. So f of z equal to e to the power 1 by z. So e to the power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. Now, so e to the power 1 by z would be equal to 1 plus 1 by z plus 1 by z square into 1 by 2 factorial plus 1 by z cube into 1 by 3 factorial, etc. This is one how you can define e to the power 1 by z. Now we need to find the residue of the function f of z at z equal to 0. So that is the coefficient of 1 by z. So coefficient of 1 by z is, here we have 1 by z here, so coefficient of 1 by z is 1. So the residue is 1. Similarly, we have the question number 2 here, which is f of z equal to z square into cos 1 by z. Again, at z equal to 0, cos of infinity, which is not defined, so the function is not defined at in that particular z equal to 0. So let's write down what is f of z once again. That is equal to z square into cos of 1 by z, then cos z or cos x. What is cos x? Cos x equal to 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial, etc. Now cos of 1 by z, cos of 1 by z would be 1 minus 1 by z square into 1 by 2 factorial plus 1 by z power 4 into 1 by 4 factorial minus 1 by z power 6 into 1 by 6 factorial, etc. Now z square into cos 1 by z, which will be equal to z square times 1 minus z square divided by 2 factorial, sorry, this is 1 by 2 factorial into z square plus 1 by 4 factorial into 1 by z power 4 minus 1 by z power 6 into 1 by 6 factorial, etc. Alright, now this can be written as z square minus 1 by 2 factorial plus 1 by 4 factorial into z square minus 1 by 6 factorial into z power 4, etc. Now that is equal to, so here we need a residue of the function f of z, again at z equal to 0. So this is at the coefficient of 1 by z. So there is 1 by z, this is z square, and This is z to the power 0, this is z to the power minus 2. There is no z to the power minus 1. So coefficient of 1 by z is 0. So residue is 0. The other kind of singularity is pole of order. Now this pole of order can be 1, 2 or 3 or maybe even more. So what does it means? That our principal part will contain a finite number of terms rather than the previous thing that we have learned. Here the principal part will contain only finite number of terms. So f of z can be written as sum over n equal to 0 to infinity an z minus a to the power n plus sum over n bn z minus a to the power minus n. Now one example where here is given f of z equal to e to the power z minus a divided by z minus a squared. This is pole of order 2. So this equation f of z can be rewritten in the form in 1 by z minus a squared into e to the power z minus a. So we have already seen how to write e to the power x, that's equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. So e to the power x as in this way. So e to the power z minus a is 1 plus z minus a plus z minus a squared by 2 factorial plus z minus a cube by 3 factorial, etc. So just multiplying by the z minus a squared, what you get is 1 divided by z minus a squared plus 1 by z minus a plus 1 by 2 factorial plus z minus a by 3 factorial, etc. It goes on. So this is the analytical part now, and these two are the principal part. So we can see that there are only two terms in the principal part, while analytical part contains more number of terms. So now we need to find the residue of the function. So residue of the function f of z at z equal to a. Now why z equal to a? Z equal to a is the point where the function is not defined. Now when you put z equal to a to this equation, it is not defined. So this is why it at z equal to a we have the singularity, and that singularity is of the order 2. That is why it is a pole with order 2. Pole simply means the singularity. Pole or the singularity has the same meaning. Now so residue of the function at z equal to a, so is at 1 by z minus a, so that is equal to 1. Now for any pole of order n, let us see, for any pole of order n, the residue of the function f of z at z equal to a can be written as we are going to see how we can write the residue in one single formula. So residue for the pole of order n is given by residue of the function f of z at z equal to a with the pole of order n is equal to 1 by n minus 1 factorial into limit z tends to a. This is n minus 1th derivative of the function z minus a to the power n times f of z. and uh, that is for nth order. For pole of order 1, residue of the function f at z equal to a, pole of order 1 is limit tends to a, z minus a into f of z. Similarly, for pole of order 2, we have residue of the function at z equal to a of pole of order 2 is limit z tends to a, first derivative, first derivative of z minus a squared times the function f of z. So we need to remember this formula. Now let's do a problem based on simple poles. Simple poles means the pole of order is 1, and the type of the question is where the denominator is having of the form of factors. So f of z is z by z minus 1 times z minus 2. So here the poles are at uh, z equal to 1, which means at z equal to 1 the function is not defined, as well as at z equal to 2 the function is not defined at these 2 points. Now we need to find the residue at z equal to 1 and the residue at z equal to 2 with both order of this z minus 1 is 1 and as well as z minus 2 is 1. So residue is of order 1. So let's do the first one at z equal to 1. So residue of the function f of z at z equal to 1 is given by limit z tends to the limit, that is 1, times z minus a, that is a is 1, so z minus 1 into f of z. What is f of z? F of z is z divided by z minus 1 into z minus 2. So that's equal to limit when z tends to 1, z minus 1 and z minus 1 get cancelled, so z divided by z minus 2. So that's equal to, at z equal to 1 means 1 divided by 1 minus 2, 1 minus 2, that's equal to minus 1. So this is the residue at z equal to 1, and now we need the residue of the function f of z at z equal to 2. Z equal to 2 means this one. So that's equal to limit z tends to 2, z minus 2 into f of z, that is z divided by z minus 1 into z minus 2. So here z minus 2 and z minus 2 gets cancelled, so limit z tends to 2, z divided by z minus 1. So when I put z equal to 2 here, that is 2 divided by 2 minus 1, that's equal to 2. So residue of the function f of z at z equal to 1 is minus 1, and at z equal to 2 it is 2. Question: f of z is equal to z square plus z plus 1 by z minus 1 squared into z plus 2. Now taking the denominator, that is z minus 1 squared into z plus 2, put it in equal to 0, we get the residue at z equal to 1 and z equal to minus 2. So z equal to 1, we have the residue which is having a pole of order 2, and z equal to minus 2 is pole of order 1. So this is 2, this is 1. Now the residue of the function f of z at z equal to 1 with pole of order 2 is limit z tends to 1, the first derivative, that is d by dz of z minus 1 squared into f of z, that is z square plus z plus 1 divided by z minus 1 squared into z plus 2. So that's d by dz of z minus 1 gets cancelled, z square plus z plus 1 divided by z plus 2 at z equal to 1. So this is u by v differentiation, so this is equal to z plus 2 into the denominator, into the differentiation of the numerator, that is 2z plus 1 minus z square plus z plus 1 into the differentiation of the numerator, that is 1 divided by the denominator squared, z plus 2 squared, and this is at z equal to 1. So 1, that is 3 into 3 into 3 minus 3 divided by 1 plus 2, 3 squared, that is 9. So 9 minus 3, 6 by 9, that is 2 by 3. So the residue is 2 by 3. Now we need the residue of the function f of z at z equal to minus 2. So that is limit z tends to minus 2, z minus z plus 2, so z minus of minus, okay, so z plus 2 into f of z, that is z square plus z plus 1 divided by z minus 1 squared into z plus 2. So that's at z equal to minus 2, so that is limit z tends to minus 2, z square plus z plus 1 divided by z minus 1 squared. So z equal to minus means 9, so that's equal to 2 minus 4 minus 2, that is 2 plus 1, that is 3, minus 3 squared, that is 9. So that is equal to 1 by 3. Now here let us look into another kind of function where the function f of z is given in the terms of phi of z by psi of z, where psi of z is a polynomial. So to find the residue of this kind of function at f of z at z equal to some point a is equal to the function phi of z by psi dash, the first derivative of the function with respect to z at z equal to a. This is very simple formula. So let's do a problem based on this. So let's write the question as let f of z be equal to 1 divided by z square plus a square. So this is the polynomial which is psi of z. Now finding the roots or equating the denominator to 0, we get z square plus a square equal to 0, which says z square equal to minus a square. This gives us z equal to plus or minus IA. So this is the values. So we have the poles at z equal to plus IA and z equal to minus IA. So these are the two poles, symbol poles. So residue at residue of the function f of z at z equal to plus IA is equal to psi of z, that is 1, divided by psi dash, that is so we'll write psi of z equal to z square plus a square, psi dash of z is equal to 2z, and that is 2z at z equal to plus IA, so that's equal to 1 divided by 2IA. So that is the residue at z equal to plus. Now the residue of the function f of z at z equal to minus IA will be equal to 1 divided by 2z at z equal to minus IA, that's equal to 1 divided by 2IA. Cauchy residual theorem. So let us assume that here we have the function f of z, which is defined in this given domain. Domain is given in this circle C. Okay. Now the function f of z, we are integrating the function over the contour or the circle f of z dz. This is equal to, assuming that it has poles or singularities at this is z equal to a, z equal to b, and somewhere here z equal to c. So these are 3 points where we have the poles z, a, b, and c. So poles at z equal to a, z equal to b, and z equal to c. Now we must uh, understand that all these poles are within this domain, and if we assume that there is another pole z equal to d, which is outside, okay, let's consider this is another point z equal to d. Now this, so these 3 poles are inside, so this inside the contour or the circle, and this is a point outside, so we need not worry about this uh, residue or the pole outside the given domain. So the integral f of z dz is given by integral over c1, which is defining the pole at a. C1 is z equal to a pole, f of z dz plus integral over c1, which is defined in the area z equal to b, f of z dz plus integral over, so this is c2, c3 z equal to c, f of z dz. Okay, so this integral is nothing but 2 pi I, and all these functions, integral over c1 z equal to f of z, integral over c2 at z equal to b f of z, and integral over c3 at z equal to c f of z dz, all are the residues. So 2 pi I into sum of residues at a, b, and c gives you the corresponding integral. So this integral f of z dz over c is 2 pi I into sum of residues. Very important formula. To find the sum or the integral, it is also important to check if the points or the poles are inside or outside. The point here means whether the pole is inside the contour or outside the contour. So if a question is given to be the circle with circle which is having the equation 4x square plus y square equal to 8, and we are given the pole at z equal to 1 plus I. Now here 1 plus I, this is equal to x plus iy. So here x equal to 1 and y equal to 1. So substitute the x equal to 1 and y equal to 1 in equation of circle, that is the above, that is equation 1. Then 4 times 1 square plus 1 square, that is y square, and check whether it is uh, less than or equal to 8. Now this is 4 plus 1 is definitely less than or equal to 8, so this is inside. Now suppose you get another question that is z is equal to 2 plus I. So z equal to 2 plus I means x equal to 2 and y equal to 1. So look at this, put it 4 times 2 square plus 1 square. So this is equal to 4 times this 2 square, that is 16 plus 1 17. So this is less than or equal to 8. No, this is not less than or equal to 8. So this point 2 plus I is outside this circle. Okay. So consider only points which are inside the contour. Now this is the question that we have solved for finding the residue. We have the residue at of the function f of z at z equal to 1, which is part of order 2, as well as the residue of the function f of z at z equal to minus 2, which is part of order 1. This was found to be 2 by 3, and here it was found to be 1 by 3. Now if you take the integral f of z dz over the contour c, and we have to define the contour c is equal to let it be x square plus y square equal to 16. So when you put x square equal to y square equal to 16, this is z equal to 1 and z equal to minus 2, which implies x equal to 1, y equal to 0, as well as x equal to minus 2 and y equal to 0. Both are well within 16. So this integral is 2 pi I into sum of residues. Residues means these are the residues. Okay, so that's equal to 2 pi I times 2 by 3, first residue at z equal to 1, and 1 by 3 at z equal to 1. So that's equal to 1, that is 2 pi I. So the integral f of z dz over c, which is c is a circle with radius 4, given by x square plus y square equal to 16 is 2 pi I.